We defined in Physics 20 a gravitational field as a region in which a gravitational force could be experienced by an object with mass. We defined an electric field last unit, and as late as yesterday when we went over our unit test from our last unit, an electric field is a region in which or let me rephrase that, a region in which an electric force could be experienced by by a charge. A magnetic field, on the other hand, is a region in which a magnetic force could be experienced by a magnet or by a ferromagnetic material. Now, just because we have a magnetic field doesn't mean there's a magnet or a ferromagnetic material experiencing it. The magnetic field is there as long as you have something to produce it. We're just saying that there would be a force on a magnet or a unmagnetized ferromagnetic material if it was there in that region in which there's the field. Does that make sense? Now, magnetic fields, of course, are caused by magnets. That's one place they're caused by magnets, right? You got a ferromagnetic material with domains aligned pointing in the same direction. Then this ferromagnetic material that has domains aligned, in other words, this magnet will cause a magnetic field. It can also be caused by moving electric charges. So charges that are moving through a wire or just moving through the air cause a magnetic field. And of course, finally, magnetic fields are vector fields, just like gravitational fields are vector fields and electric fields are vector fields. There is a direction associated with the influence. If you have a magnetic field, just like an electric field is going to influence a positive and a negative in a certain direction, a magnetic field is going to influence a north pole and or a south pole in a particular direction as well. So it's a vector field. It influences in a particular direction. Make sense? Okay, we're going to spend a few minutes here now as groups, in groups of, we'll go groups of 3 or 4 because of the size of your class here, doing a little activity, not a hand-in activity, just an activity that we're going to use to plot electric fields, to discover, I should say, the magnetic fields that surround various configurations of magnets. The handout that I gave you guys last week, first page of it shows 3 different configuration of magnets. The first one is when we have a north pole and a south pole. Second one is we have 2 magnets beside each other, a south pole nearby a north pole, as you can see there. And the third configuration is when we have 2 magnets, a north pole against a north pole. Does that make sense? What you're going to do with your group of 2 or 3 people is to take a magnet or magnets, depending upon what the scenario looks like, and replicate that scenario on your desk. Now, I want you to make sure that when you're doing this, you put the magnet, can I just borrow your desk for a second? I want you to put the magnet in the middle of the desk. You can still sit there if you want. Put the magnet in the middle of the desk. Don't put it near the edge of the desk because then it's going to be influenced by the ferromagnetic desk legs. Put it towards the middle of the desk so that it's influenced as little as possible by those desk legs. Does it make sense? Don't put your template, your piece of paper underneath the magnet. It's not the same size. The piece of paper that I gave you is just a map. It's not to the same scale as the actual magnet is. Just look at it as a map. And if on your map, your template that I gave you, it says the south pole is on the right side, then make sure the silver end of the magnet, the south pole, is on the right side. If you see this one in your little template or your map, then you're going to want to make sure that you have a south pole like this on your desk and a north pole, the red end, like this on your desk. Does that make sense? Each of these stars represents a spot where I want you to put a compass, like a compass that you use for navigation. If you're in the woods, use a compass for navigation. Okay, you're going to put a compass in those spots. Again, don't put the piece of paper on your desk and try to put the compass literally on those spots because the scale is wrong. I just want you to use this as a map. If there's a spot right here between the North Pole and a South Pole, then I want you to put the compass in between the North Pole and South Pole of your magnets and then look at which way your compass needle is pointing. If your compass needle points to the right, then draw a short little arrow to the right. If your compass needle points to the left, then draw a short little arrow to the left. Just make it short, because we're going to do something with these diagrams later that depends upon these arrows being short. I want you to do that for all of the stars. So use this map, the three different configurations of the magnets, to determine which direction the compass needle points in all of these spots for all three different configurations. Does that make sense? Now that everybody's finished collecting their data for this, let's put it together and see what we should get for the patterns that we're trying to form here. In your first diagram, we have a north pole on the left side and a south pole on the right side. You should have gotten something like this. It's not going to be exactly the same as mine, but as long as it looks more or less the same as mine, that's good enough. We should have had a little arrow pointing this way, and pointing this way, and this way. Does yours look something like this, everyone? Okay, if it looks something like this, more or less like this at least, then you got what you were supposed to get. Let's do a little grade 1 work now and connect the dots. This is where I'm going to give you a hand so that you know which dots to connect. Should look something like this. You can see that the magnetic field, which is what we drew as the tip of the compass needle, the magnetic field is pointing this way, toward the south and away from the north. We'll talk more about that in a moment here. Now, this might remind you, maybe you notice a pattern here, maybe you don't notice a pattern. Either way, it's okay. But this might remind some of you, at least, of a diagram that we do in our last unit for electric fields. If we had, you don't need to draw this second diagram if you don't want to. If we had a positive charge and a negative charge, the electric field surrounding those two charges would look something like this. Away from the positive, toward the negative. Now the difference here is that the electric field would be from positive to negative in between here as well. The magnetic field inside of the magnet actually goes the other way. It goes in the direction that the domains would point. The magnetic field outside points from north to south, but the domains point from south to north. And those domains are effectively extensions of the magnetic field, so they're going to point from south to north inside. It looks almost exactly the same as a positive and a negative, the electric field surrounding that positive and negative, except directly in between the two poles. Now, the second scenario that you guys drew looks something like this. North pole and a south pole against each other. Your little arrows, which are representative of the magnetic field lines at particular spots, are going to look something like this. Did it look something like this for you guys? Not necessarily exact. You might have found one or two of them, depending upon where the exact placement of your compass was, one or two of them that looked a little bit different. That's okay. We just want to see the general pattern. We start connecting these dots, it's going to look something like this. From north to south, outside of the magnets, from north to south, and then it continues going around like this. These aren't perfect, but that's okay. Close enough. It's going to look something like this, which might remind you of something that you drew in our last unit. If we had a negative and a positive, the electric field lines would look like this. Okay, looking a lot like the north and the south there. If we stuck another positive in here, it would look like this. If we stuck another negative in here, it would look like this. Starting to look an awful lot like the magnetic field lines between the north, south, south, north, or between the north, south, north, south, I should say. The difference, once again, is the electric field lines right here go from positive to negative. The magnetic field lines right here go from south to north. So right here, we're going from north to south, but that's outside of the magnets. Right here, we're going from south to north because that's inside of the magnets. Really, inside the magnets, we're looking for the direction of the domains, which we define as being from south to north. Now, I got one little thing here that I didn't fill in. Field lines join. What do I mean by that? You see these field lines joining in between the North and the South Pole. What do you think that means? When field lines join, you're going to get a force of attraction, yeah. Just like in the last unit with electric fields, you look for a couple things, okay? Direction of the magnetic field, but also if the field lines join up, we get a force of attraction. If they don't join up, we get a force of repulsion. The last diagram that you drew, where we had north against north, we should have gotten field lines that looked something like this. Something like this, at least. And if we just start joining those together, it's going to look something like this. Which again, if you put a positive and then a negative and then a negative, you would get an electric field that looked pretty much the same as this, except that in between this negative and this positive, the field would go from positive to negative. Here, the field inside, because it's inside the magnet, is going from south to north. Remember, outside the magnet, we're going from north to south. Inside the magnet, we're going from south to north. Field lines don't join up here. You can see in the middle that they're clearly not joining up. They're repelling each other, which means that when they don't join, just like with the electric fields, we get a force of repulsion, yes. So we're going to define, after this activity now, we're going to define the direction of the magnetic field in two ways, kind of like we defined the direction of an electric field in two ways. We defined an electric field direction as the way that a positive particle would move if placed in the field. Well, this is almost the same, except it's the direction that a compass needle points when placed in the field. Specifically the north tip of the compass needle, which is typically the red tip of the compass needle, right? So whichever way the red tip of the compass needle points when placed in the magnetic field. Now, the other way to define direction of an electric field was away from the positive toward the negative. The other way we define magnetic field is away from the north toward the south. That is, assuming you're outside of the magnet. If you're inside of the magnet, it's opposite, right? It's from south to north. But typically, in almost everything we do, except for one thing that we'll do here in several days, in almost everything that we do, we're looking for the magnetic field outside, not inside of the magnet. Okay? Some little summary table here now. We got three fields that we've learned about so far. The cause of a gravitational field, of course, we know this, right? It's a mass, yeah. Now, somebody this morning said a really heavy mass. Well, really light masses cause gravity fields as well, just not as strong, right? Every mass causes a gravitational field. Even an electron causes a gravitational field. It's just a really weak gravitational field. Stronger masses cause stronger gravitational fields. What causes an electric field? Electric charge, yeah. What causes a magnetic field? Normally we would say a magnet. But we know, we haven't learned much about this, but we know that moving electric charges, or in other words, electric current, can cause a magnetic field as well. More on that comes tomorrow, actually. What's the direction of a gravitational field? Well, there's two ways we define the direction of a gravitational field. One, we define as the direction that a mass moves in the field. If you put a mass in a gravitational field, it moves in the direction of the field, down toward the producer. An electric field is defined as the direction that a positive moves in the field. The magnetic field is the direction that the compass needle points. Now, technically, we're talking about the north tip of the compass needle, but whatever end you're supposed to be looking at, which is defined as the north end, that's the way that the magnetic field points. Now, what's the second definition of the direction of a gravitational field? Toward the producer. Toward the thing that causes the gravitational field. Oops, I numbered these wrong. This should have been 1 and 1, right? Not a big deal. What's the second definition of an electric field? Well, not toward the producer necessarily. It's toward the negative away from the positive producer. How do we define the second definition of direction of the magnetic field? It's toward the south, away from the north. That is, if we're talking about outside of the magnet. If we're talking about inside of the magnet, it's the opposite, right? It's toward the south, toward the north, and away from the south. Now, I got a map, I got a diagram of the Earth here. I want you to notice a couple of things, and I'll point what I want you to notice here. The Earth has a North Pole and a South Pole. But look at how we define the direction of the magnetic field. We define the direction of the magnetic field in two ways. First, the direction that the compass needle points when placed in the field. If we look at the equator, which is right here, and we put the compass needle at the equator, it's going to point this way, right? But we also define the magnetic field as away from the north and toward the south. That means that the magnetic field surrounding the Earth is not actually as we usually describe it. We say the North Pole is in Canada, or it actually used to be magnetically in Canada. Now it's not actually, it's moved, it's shifted. It's outside of Canada now. But we used to say the North Pole, the magnetic North Pole is in Canada. Now we say it's close to Canada. It's not really, actually. Magnetic South is Canada. Magnetic North is Antarctica. It's exactly the opposite of geography. Geographic north is northern Canada. Magnetic north is not northern Canada at all. It's Antarctica.
Everything backwards in science.
I don't know. Now, what kind of implications does that have? It doesn't really matter. It's a definition, right? It's the way we define the direction of the magnetic field that results in that. But I'm telling you this. If when you were 5 years old, you asked Santa for that Lego set, that really cool Lego set, and you didn't get it, I'm telling you why. Because you sent your letter to the North Pole. The penguins are probably still laughing down there, reading that letter saying, he wanted that Lego set. And
we need to melt the ice caps.
Exactly.